Hello everyone. This video covers sections 1.8 and 1.9. So let's start with section 1.8, which is change of variables. So let's start with the definition. A function of two variables is said to be homogeneous of degree m if the following is true for all values of t for which the order pair is in the domain of f. Now, are going to focus only on the case where the value for m is equals to 0. That means that for our purpose, homogeneous of degree 0 is going to be this. The f of tx, ty is just equals to f of x, y. Now, don't forget that y prime is technically another name for f of x, y. So for our purpose of this section, this is what we're going to focus on. And therefore, the method we're going to use is going to work only for homogeneous functions of degree 0. Now, if you remember from the last two sections, we've been solving differential equations of this type. So what we're going to do a change of variable, hence the name of the section. And we're going to change from dy dx to a function. We're going to try to find a function where we're going to introduce a new variable, which is going to depend on the value of y and x. And the new variable is going to be v. So v is going to be equals to y over x. So this will be the substitution or the change of variable. Now, don't forget that y is technically still a function of x. So from here we have y is equals to x times b of x. So if we take the derivative in both sides with respect to x, from here we will get dy dx. Then here we're going to use the product rule. So this will be the derivative of x, which is 1 times b plus x times dv dx. So again, this is just the product rule from calculus. Okay. Notice that the point of doing this substitution was that we want to introduce a new variable, which is going to be the variable b. So therefore, from here, you can also say that dy dx is just equals to a function that depends only on v. But this is the part where to be careful. Dy dx is equals to this, but dy dx is also equals to this part. So therefore, if you combine this one in here, we will get the following. We will have the b plus x dv dx is going to be equals to some function that depends only on b. This is actually a separable equation, like the ones we did at the beginning of this chapter. This is what I mean. This is the same thing as this. So notice how the right side, it depends only on the variable b. So you can separate the variables, and you will end up with dv over a function of v minus b equals to dx over x. And then to solve the problem, all you have to do is integrate. Okay. Now, here are the good news and then the bad news. The good news is that this integral is always going to be ln x, so it's going to be easy. This one is going to depend on what this function is. So this could be tricky and it could take a while. But again, this goes back to just using the integration techniques from calculus 2. But it's important to notice that pretty much you're always going to end up with something like this, which will lead to something like this all the time. Okay, so let's do an example. Remember that the goal is to have y prime is equals to a function that depends only on b, where b is equals to y over x. Don't forget that this is the substitution. So there is multiple ways to do this, but since you want to end up with y over x, for this particular example, the easiest thing is to divide everything by x, or both sides. So if we divide both sides by x, we will end up here with 3 minus 2b dy dx, and in the other side is going to be 3b. Why? Because y divided by x is b, y divided by x is b, and x divided by x is just the number 3. Right? Then, if you solve for dy dx, this will be equals to 3b divided by 3 minus 2b. Now, recall just from the last page, let's go back to the last page. When we do this substitution from here, you can say that dy dx is going to be equals to v plus x dv dx all the time. We talked about that already. So therefore from here we substitute this for this, so we will have b plus x dv dx, and in the other side we already have 3b over 3 minus 2b. Again, notice how this is just y prime, and this is the function of b. From here on, it will depend on what this function is, how tricky it's going to be to integrate this part. All right, so from here, then we can see that if we solve for dv dx, or if we just move the b to the other side, we're going to end up with something like this. So from here we have the x dv dx is going to be equals to 3b over 3 minus 2b minus b. Then if you do a little bit of algebra here from basic algebra, and you should stop the video and check that this is the case, you will get x db dx equals to 2b squared divided by 3 minus 2b. Again, you should check that, you should convince yourself that that's what it is. Then if we separate the variables, you will end up with 3 minus 2b over 2b squared equals to dx over x. Okay, again, notice the 3 minus 2b over 2b squared, and this is just basic algebra. This is equals to 3 halves times 1 over b squared minus just 1 over b. So therefore, if we integrate both sides, well, the integral on the left side is, on the right side is easy. It's just ln x, like I told you. That will be the case all the time. Now the integral of this part is just minus 3 halves times 1 over b, and then minus ln of b, which will give you minus 3 over 2 times x over y. If you switch back from b to x and y, minus ln of y over x equals to ln x plus c. Now here notice the, again, ln y over x from precalculus is the same thing as ln of y minus ln of x. And the minus here, and the minus is going to make a plus, which means that this is going to disappear. It's going to cancel. So this is going to go away with this one. So what you have left, it will be negative 3/2 x over y minus ln of y is equals to a constant. And that's it. Here you can solve for y explicitly, so just leave the answer like that. Now, one last thing to notice about this part, the answer after here is the solution in terms of v and x, but the original question is in terms of x and y, so that's why you had to undo the substitution until you end up with x and y only. All right, well, you didn't get that one. It's a chance to redeem your sins. Let's try one more time. Okay, for this problem, first let's try to have y prime by itself, so we subtract y ln x. Notice that here you can factor y, so this will be ln y minus ln x by using this same formula from precalculus. You can go from here to here, you can go from here to here too. So therefore, here we factor the y. We can rewrite this part as just x times y prime equals to y times ln of y over x, which is a good thing, because remember we're trying to have y over x because that will give you b. Now if we divide by x now, that is going to give us exactly what we're looking for. So we're going to have y prime is equals to b times ln of b. But remember that y is going to be, for these particular problems, always equals to vx dv dx. And in the other side, you have a function that depends on b only. Remember that this is an equation that you can always separate. So from here, we're going to have x dv dx equals to v ln b minus b. So you can actually factor the v, so this will be ln of v minus 1. And then if you separate the variables, you should check this, you will end up with dv b ln of v minus 1 on the left side. And on the right side, I told you this should always give you just the x over x. All right, so the next question is, well, how do we integrate this part? This one is pretty easy, okay? So this is what we have to do. So let, you don't have to do it this way, but this is probably one of the easiest ways. Let the new substitution u equals to ln of v minus 1. So that means du is going to be dv over b. Notice that that is equivalent to this part right here. So this will be the du, and this part here will be the du. So therefore from here we end up with du over u, and on the right side we have a very easy integral. So therefore in this particular case the left side will be ln of u equals to ln of x plus c. Now, to make our life easier for this particular example, remember, since z is just c is just a constant, then ln of z is also a constant. So it will be more helpful to write it this way to make the algebra easier to simplify, because if we call this ln c instead of z, on the right side we're just going to have ln of c x. Instead of having two members, you only have one element now. Now here you have to be extra careful now, because you have u, which is a function of v, and then b you have to change it back to x and y. So this is what we have so far. This is equals to ln of ln b minus 1. Now the reason why I choose to write this as a ln 2, because now you can see you have ln in here, you have ln in there. You can cancel each other out. So you will end up with just ln b minus 1, and the other side will be the constant times x. So therefore from here we have ln of b is equals to 1 plus cx, or ln of y over x is equals to 1 plus cx. And from here you can change from log to exponent, so we have e to the 1 plus cx is equals to y over x, which means the y is equals to x e to the 1 plus cx. And this is the final answer. All right, well, if you still didn't get the last two examples, here's your last chance. Here it is. So this is the new question, and again, all of these are homogeneous, so degree 0. So you can check them if you want, but there's no need to. So let's start by dividing by x on the right side. So if we do that, remember that this one is going to be b plus x dv dx. So we have done this now 2 times, so it should be obvious now. On the other side, now it's going to be 2 minus b, and this is going to be 1 plus 4 b. Okay? Then we're going to combine the b's and x, or separate the equations. So we're going to have db dx times x is equals to 2 minus b over 1 plus 4b minus b. And then you should definitely check the right side is going to give you 2 minus 2b minus 4b squared over 1 plus 4b. Okay, again, you should definitely check that. Stop the video and convince yourselves. Then if we separate the variables, which we did that for the last 2 examples, we'll end up with the integral of 1 plus 4b, all of this db, divided by 2 minus 2b minus 4b squared equals to the usual dx over x. Now this integral looks a little more threatening or annoying than the previous ones. So therefore, notice the following. There is not a unique way to solve the integral, but this factoring is going to make life a little bit easier, and this is what I mean. Notice that 2 minus 2b minus 4b squared is the same thing as minus 2 times, you can have here 2b squared plus b minus 1. Again, it's not required to do this, but it will make integrating a lot easier. And you'll see why in a second. So my point is that we can rewrite this part now as this. So on the left side, we will have 1 plus 4b divided by 2b squared plus b minus 1 dv, and then the negative 2, we just put it on the other side. So this will be minus 2, the integral of dx over x. Now, the only reason why I did that is because then it will make integration very easily. And this is what I mean. So now if we let u to be 2b squared plus b minus 1, then du will be 4b plus 1, which is exactly on the top. So therefore, from here, we will get a du over u, and this will be equals to minus 2 dx over x. And again, we do the same trick. This is ln of u. This will be minus 2 ln of x plus, remember it's a constant, but to make our life easier, again, we'll just call this ln c. And on the left side, now we have ln of u, but remember u was equals to 2b squared plus b minus 1. And on the right side, if you use the properties of logs, this will be ln of c over x squared. Why? Because remember the log property says the following: log of a to the r is equals to r log of a. Okay, so these are just properties from pre-calculus. Now, since you have, again, log in here and log in here, you can cancel them out. And from here, we get 2b squared plus b minus 1 is equals to the constant over x squared. And then we get a 2 y squared over x squared plus y over x minus 1 is equals to c over x squared. Now, if we plug in the initial condition, remember the initial condition is going to give you the value for z. So y of 1 is equals to 1. So from here we will have the 2 times 1 squared over 1 squared plus 1 over 1 minus 1 is equals to c over 1 squared. And from there you can tell right away that c is equals to 2. And if this was a question on the exam, you can just leave it like this once you find the value for c. The last example we're going to do is it's a completely different substitution, but it's a very interesting case and it's a very famous equation too. So we're going to do one more example before we go to the next section. All right, so for the last example of section 1.a, we have something very specific called Bernoulli's equation. And notice that this is very, very similar to the linear equations where we use the integrating factor. And actually, we're going to kind of use the integrating factor to solve this question. There is a big difference here, though. Now, the big difference here is that this equation is not linear because of this. Okay? And therefore, since this is not linear, the integrating factor doesn't work. So we had to do a substitution or something else. So the substitution we're going to do is going to be this. U is going to be the new variable. It's going to be equals to y to the 1 minus n, where n will be whatever this value is. Now, I'm just going to give you the equation. You're going to end it from here, but it's a very good exercise to get the answer. Once you do this and you use the product rule, actually the chain rule, you will end up with something that looks like this. du dx plus 1 minus n, and then p of x, which is the same be from here u, and then this will be equals to 1 minus n qx. And the important part is that now this equation is linear, so this is going to give you this. So this is linear, and therefore that means you can just use the integrating factor method that we used before, and then just change back to y from u. Again, it's a very good exercise to check that this is the case. All you have to do is use the chain rule from calculus in this function. All right, so let's look to the example here. So notice that this equation obviously is not going to be linear, and this is the reason why it's not linear, because it has a y on the right side. And here the value for n is actually equals to -1. Okay. So therefore, if we use the formula here, notice that since n is equals to -1, then the substitution is going to be u is equals to y to the 1 minus 1, which will be y squared. Okay. But you can go straight to this and solve this equation, and this is what I mean. So from here, we're going to get that du dx minus 1 minus 1, which is the value for n, times p of x. Remember that p of x is 1 over x. That's why we have the minus here. Actually, maybe I should write that down. Here, p of x is equals to minus 1 over x, and q of x is equals to 4x squared cosine of x. Okay. All right, so therefore times u, and this will be equals to 1 minus 1 times q of x, which is going to be 4x squared cosine x. Okay. Then if we simplify this, we will end up with du dx minus 2 over x times u. This is equals to 2 times 4. It will give you a x squared cosine x. All right, so now we can use the integrating factor in this equation. So we can use the integrating factor, and the integrating factor in this particular case is going to be e to the -2 over x dx. Now we did this a few times. Remember, you have to be careful with this part because this is technically e to the -2, the integral of the x over x, which is e to the -2 ln x, and you have to be very careful here. This is e to the ln x to the -2, which is technically x to the -2, or 1 over x squared. Okay. So we did this before. Remember, all of this part, all of this is going to be the integrating factor, which is x to the -2 times u prime. This is identical to what we did in the last class, or the integrating factor. Now, if you divide by x squared, clearly the x squared is going to disappear. So therefore, on the right side, you only get a cosine of x. So then, if we integrate both sides, remember with the integrating factor method, what happens is that this cancels down. So we will end up with x to the -2 times u is equals to a sine x plus c. All right, now if we solve for u, that means that u is equals to x squared or ax squared sine of x plus c x squared. But remember that u was equals to y squared. So therefore we have y squared is equals to a x squared sine of x plus c x squared. And then you can take the square root, so it will be plus or minus the square root of, I guess you can factor the x squared. This will be a sine of x plus c. This is plus or minus the absolute value of x times the square root of a sine of x plus c. And that's it. So y will equals to that. Again, this is a very specific case, which is called a Bernoulli equation. So you only use this substitution if the question is asking to solve a Bernoulli equation. All right, so that's it for section 1.8. All right, so now let's go to section 1.9. And these are called exact differential equations. You may actually have done this. It's possible that you may have done this in calculus 3. But if you haven't, it's not a big deal. We will go over this right now. So this is the definition. A differential equation, so I'm going to use the E from now on to always say differential equation. This form is supposed to be exact, or is supposed to be exact if there is a function phi. So this is what we're trying to find. So this is what we want. Okay, so this is what we want to find, where the partial of phi with respect to x is equals to this function, and the partial of phi with respect to y is equals to the second function. This is actually related to the differential from calculus 3. Remember, in calculus 3 they will ask you to find the differential, and the differential of a function was equals to this. And you can see this is exactly what we're gonna try to find here. Okay? And therefore, if the derivative is equals to 0, that means that this is actually a constant. Okay? Now, there is an easy way to check if something is exact, and it's we're going to do it. So this is the test for exactness. If the partial of m, which is whatever it is in front of the x, with respect to y is equals to the partial of n with respect to x, then the equation is exact. If this fails, then the method we're going to use doesn't work. Now, the last example we're going to do is not exact. So there are specific cases where if something is not exact, you can change it into an exact equation. But if you cannot change it into exact equation, then this method doesn't work at all. So the first thing you should check is to see if the equation is exact. And if it's not exact, unless you can make it exact, there is no point to use this method. Now, before we solve a problem, so let me tell you the general idea how we're going to solve this. First, you check to see if the equation is exact. Once the equation is exact, you're going to pick either the partial with respect to x or the partial with respect to y. So either one you pick, it doesn't matter. So let's say that you pick this. Remember, the goal is to find phi. So how do we find phi? Is by integrating. So you integrate both sides. The big difference is that this is a partial derivative, not a derivative. So when you integrate, the constant you're gonna get, it is gonna depend on the second variable, which in this case will be y. Then you're gonna take the derivative of that with respect to y and make it look exactly like we have here. And if anything is missing, that will be the value of the constant. So this is actually pretty simple. This is probably one of the easiest methods we done so far. Sorry, just have to be careful with that. Again, first check if the equation is exact. Once you pass that step, pick either this one or this one, integrate, and whatever you get is going to have now a function, a constant that it depends on the other variable, and you have to make sure that you solve for that constant variable. All right, so let's do an example, and hopefully this will make sense. So here it is. So this is what we have so far. So here, this is going to be m of xy, and this is going to be n of xy. Now, it may be more helpful to actually write it out. So m is equals to sine y plus 1 cosine x, and then n is equals to sine x plus x cosine y. All right, so first thing is check for exactness. Now, what's the partial of m respect to y? Derivative of sine is cosine y plus cosine x, because the derivative of this respect to y is just cosine x. Now, what is the partial of n with respect to x? Derivative sine is cosine x, and the derivative of this part with respect to x is just cosine y. So clearly, m of y is equals to n of x. So that implies that this is exact. So that's good. Now again, remember that this is the same thing as d phi dx, and this is d phi dy. You have to pick any of them. It doesn't matter which one, but to keep it simple, let's go with the first one. So if we select this one, then we have d phi dx is going to be equals to sine y plus y cosine x. Okay, then we integrate. Okay, so integrate with respect to x. So it's very important that you understand this part. So if we integrate with respect to x, on the left side we'll have phi of x and y. Now the integral of sine x with respect to x is going to be just x sine of y, and the integral of y cosine x with respect to x, it will be y sine of x plus a constant, but the constant is now going to be a function of y. Why do we need to have a function of y? Well, if you take the derivative of, let's say the derivative with respect to x of phi y squared is equals to 0, right? So that's why you have to make sure that this is the proper constant. So you cannot just write c anymore. So this is the part that is new, and then you have to be very careful about. Usually once you figure out what this is, then you're done. This is how you're going to figure out the value for the constant. Remember that the partial of y, the partial of phi with respect to y is supposed to equals to this. So therefore, the partial of phi with respect to y has to equal to n. Remember, where n is equals to sine x plus x cosine y. So therefore, if we take the partial of phi, which will be this. So if we do the partial of phi with respect to y, then what the derivative of this with respect to y is going to be x cosine y, and the derivative of this with respect to y is going to be sine x plus h prime of y. Notice that this part is exactly to this part, and since you want both of them to be equal to each other, what this implies, you have no choice. That means that h prime of y has to be equals to 0, which means that h of y has to be a constant. And for lack of a better name, just call the constant 0. And that's it. So therefore, that means that the solution is equals to x sine y plus y sine x. And that's it. Now, many times the value for this is equals to 0, but it's not always the case. That's why you have to check. So you should not assume that because the first example, or even if the second example is equals to 0, that will be the case all the time. It just happens here that it's equals to 0. All right, let's try one more. So here I just identify that this is d phi dx, and all of this is d phi dy, or remember that this is also m, so m is equals to y over x, and n is equals to 1 plus ln x plus ln y. It's easier to write it like this. You'll see why in a second. Right, so first you have to check for exactness, otherwise there's no need to keep doing this. So the derivative of m with respect to y is equals to 1 over x, and the partial of n with respect to x is equals to 0 plus 1 over x plus also 0, which is 1 over x. So we have the following, that m of y is equals to 1 over x, which is equals to n of x, so that implies it's exact. So this is good. All right, so next, remember you can pick either one, d phi dx or dy dx. So we did this one before, so let's do this one more time, but if you pick this, you should get the exact same thing. So we have d phi dx equals to y over x. Now remember, we're integrating with respect to x. So if we integrate with respect to x, we get the following. On the left side, we will have phi of xy, but on the right side, we will have y ln x plus, let's try x, plus some constant that depends on y. Remember that the only thing we need to figure out now is technically what is this value for h of y. Okay, so this is what we need to figure out. And we know that if we take the derivative of this with respect to y, it should give you exactly this. So let's do that. So therefore, the partial of phi with respect to y, in this particular case, it will be ln x plus h prime of y. And remember, this needs to equal to 1 plus ln x plus ln y. Therefore, in this case, you can see that this is not equals to 0. This implies that h prime of y has to be equals to ln of y plus 1. Now, since we want to find h, then we integrate with respect to y. So now we integrate with respect to y. And this is a classic integral. You use integration by parts. This will give you y ln y minus y. The integral of this one is going to be plus y, and then plus some constant, which again you can just let it be equals to 0. So therefore the value for each y is just going to be y ln y, because these two will cancel. Hence the value for phi, which is what we're trying to find, that means that phi of xy is equals to y ln x, which is what we have so far in here, plus HOY, but HOY is now just y ln y. And this is perfectly fine, but you can factor y, and this will be ln x plus ln y, and most likely the answer on the back of the book is going to be like this: phi of xy is going to be equals to y times ln xy, and that's the answer. Now, what happens if the equation is not exact? Now, there are two very particular examples where if the equation is not exact, so if the equation is not exact, you still can make it exact, but you only have two cases. If you do the partial of m with respect to y minus the partial of n with respect to x, and you divide by n, and you end up with a function that depends only on x, then you can use the following integrating factor, and this will make the equation exact. The other case is this: if this partial minus this partial divided by m is a function that depends only on y, then this will make the equation exact. And once the equation is exact, then you can use the exact same method we used in this problem and the previous one to solve the equation. If this is not the case, then you cannot solve the problem using this method. All right, so let's try this example. So here m is equals to xy minus 1, and n is equals to x squared. So let's check for exactness, and notice that the partial of n with respect to y is x, and the partial of n with respect to x is 2x. So clearly x is not equals to 2x unless you are a politician or something. So clearly this is not the case. So this implies that the equation is not exact. Okay? But remember, you still have hope, and the hope is this. So now notice, okay, that the partial of n with respect to y and the partial of n with respect to x over n give us the following. This is x minus 2x over x squared, which is equals to negative 1 over x, which this is a function that depends on x only. So therefore there is hope. From here we find the integrating factor. Remember, the integrating factor will be e to the minus 1 over x dx. We have done this now multiple times. This is e to the minus ln x, which is equals to e to the ln x to the negative 1, or just 1 over x. Now minus 1 over x is 1 over x. So therefore, if we multiply the whole equation, the original equation, by this, and this is what I mean by that. This is the original equation, xy minus 1 dx plus x squared dy is equals to 0. So if we multiply this by the integrating factor, okay, notice what happens. So then here we end up with y minus 1 over x dx plus x dy equals to 0. All right, and then now this will be the new m. We're gonna call it m hat, and this will be the new n. I'm gonna call this m hat, and we do the same process again. So we check for exactness again. Okay. Now notice that the partial of this one now with respect to y is equals to 1, and the partial of the second one with respect to x is also equals to 1. So that implies that it is exact. All right, so after this point, we do exactly what we did before. So d phi dx, remember, is equals to n. So this is the new n we have. So if we integrate with respect to y, we'll end up with phi of xy is equals to xy. So we integrate with respect to x minus ln of x plus some constant that depends on y. Then remember, if you take the derivative of this with respect to y, it's supposed to give you x. So from here, it follows that the partial of phi with respect to y is equals to x minus 0 plus h prime of y. Again, since x is all you need, that means that h prime, just like the first example we did, h prime of y has to be 0, which means that h of y is a constant, but for lack of a better name, just use the value 0. And therefore, the solution for phi, so phi of xy, is going to be equals to xy minus ln x plus 0. And that's it. So this is the answer. Which, remember, all of this is supposed to be a constant if you take the derivative and get 0. Okay, but you just have to write the answer like this, and you're good. All right, so that's it for section 1.9 and exact equations.